Hello everyone, my name is Matthew Rocklin, and today I'm going to talk about deploying Rapids and Dask at scale. This is going to be talk both about the opportunities that GPUs can bring to sort of data science machine learning, but also about the challenges of getting it right. We're talking actually more about the challenges and opportunities. So what we often see today is that many companies have big data machine learning problems, which is fairly common today. They also have recent access to lots of GPUs. This might be 10 machines they recently bought, each with 4 to 8 GPUs each. Or this might be access to some cloud system, where they sort of want to start playing with GPUs that are available through that cloud access. They're usually sort of curious about where to start, or sort of trying a bunch of workloads that are pre-existing in their company, seeing which work and which don't work. And they may be hitting some speed bumps along the way. They may not be getting the same kind of performance that they've seen in talks like this one, and they're sort of curious why. So the point of this talk is to help you build some intuition about what's happening and why you might not be getting perfect performance, and try to get some feedback on how you can get better performance and really make those GPUs sing for you. A brief bit about me. I've been in the open source Python space for a really long time, sort of the data science side. I worked at Anaconda for a long time, where we started the Dask project, where I'm one of the lead maintainers. Dask is a library for parallel computing in Python that's pretty broadly adopted today. Then we moved over to NVIDIA Rapids, where we built out the sort of Dask Rapids a multi-GPU effort. And then I very recently founded Coiled, which is a company that sells software to help you manage Dask and Rapids on the cloud or on-prem. We also sell some support for companies who are looking to get started, maybe like you. Okay, so let's talk a little bit of background on Dask and Rapids, then we're going to do an example, then we're going to talk about how everything breaks. So Rapids is a suite of software libraries that were designed to provide GPU-accelerated data science. If you are familiar with Python libraries like NumPy, Pandas, scikit-learn, or XGBoost, Rapids helps to provide GPU-accelerated equivalents of those libraries so that you don't need to learn how to use CUDA. You can just use Python libraries and swap out Pandas for Rapids cuDF, for example, to do data frame manipulations. What we've found is that GPUs are really exciting for deep learning. They're also exciting for a lot of data science use cases. Things that might be more mundane, but also maybe more common. Things like parsing CSV files, or merging data frames, or doing logistic regression, or gradient boosted trees. So Rapids really helps accelerate all of those, originally on a single machine, and you combine it with Dask, you get multi-machine, multi-GPU acceleration. So Dask isn't GPU specific. Dask actually was made several years ago, originally to parallelize NumPy and Pandas, but it's grown to lots of other libraries since then. Dask provides distributed computing in Python at a relatively low level, and then it has lots of integrations with popular libraries. So if you want to use NumPy on 50 terabytes of data, you can do so with a Dask NumPy library, Dask array. There's many things like that. And what's really exciting is that you can now use Dask and Rapids together to use not 100 CPUs, but 100 GPUs, or 1,000 GPUs across a cluster. And now you can start doing some really exciting, really high performance things, all while still in the comfort of Python, from a Jupyter notebook, with the same skill set that you probably already have, with a few twists. So Rapids provides really fun acceleration. Libraries like Dask, along with Rapids, also provide integration to lots of libraries in the Python data science ecosystem. And it's really exciting seeing how many of these are coming on very rapidly. We actually just added Optuna like a week ago, so we'll see a demo with that later today. But there's lots of fun things out there. This is a small sample. And what this means is that Dask combined with Rapids, combined with Jupyter and the rest of the Python ecosystem, provide a really both high performance platform for analytics, but also a really high productivity platform. You can do lots of different things with lots of different tools, like Jupyter Notebooks, like what we just saw, but also interactive image viewers like Napari, or various dashboards or real-time streaming systems. There's a lot of things that are out there if you want to go and play. So that's what most Rapids talks looks like, or most Dask talks look like. We give you some cool demos, we show you some great performance numbers, and you go and you're excited to try it out. We're now going to go and try something out, and it's not going to work exactly as planned. So I want to go through that experience with you. And maybe you've also seen that experience in your own efforts. So we're going to play with XGBoost and Dask and Optuna, and we're going to swap out CPUs for GPUs. So Optuna is a library out of Preferred Networks, which does hyperparameter optimization. It's very popular, and it gives you a lot of flexibility. James Bourbeau, a Dask maintainer, integrated Optuna and Dask just, I think, a week or two ago. And so we're going to try a demonstration that isn't quite as polished as you normally see in these talks. And we're going to try hyperparameter optimization on top of XGBoost with GPUs. So let's go and try that out. So I have taken here the sort of standard Optuna example with XGBoost, and we have connected up to a Dask cluster on the cloud. And this cluster has CPUs attached to it. So we've got, it looks like 10 machines, each with a few cores and some RAM. And then we're going to use Optuna and Dask together to do some hyperparameter optimization. So while that's running, let's go take a look at this code briefly. So up here, we've got some parameters that we can use, right? And there's a space of parameters that we might want to try, right? There's some different models we might want to try, some different algorithms we want to try choose between, and some numeric parameters. And Optuna is giving us a framework to select from those and find the best ones. The rest of this code is XGBoost, right? We're training, we're predicting, then we're evaluating accuracy. And so that's relatively straightforward. We got to run many trials in parallel on this cluster on AWS, and we're seeing all those trials here. Looks like each trial is taking, 10, 20 seconds, something like that. We ran 50 on as many cores, in about 30 seconds. So this is the kind of algorithm that you might be running into at home or at your workplace. You're probably doing something like this today. Now you're excited about GPUs, you want to try out a GPU cluster. Let's go ask for that cluster. So we're again using the cloud here to get a machine of about half as many workers. We're using T4s in this case. T4 is sort of a relatively efficient, cost-effective GPU. They're about twice as expensive as an equivalent CPU node, so I'm scaling back the number of workers to about half what we had on the CPU side. Let's switch our dashboard plots over to that new cluster. And we can see here, rather than 10 machines, we now have just 5. But these machines, again, have a little bit more hardware in them. We're also going to make a different change. We're going to change XGBoosts and ask it to use a GPU accelerated algorithm. I found these two lines in, I think, some Rapids notebook somewhere that was talking about GPUs and XGBoost. I actually don't really know how the best way to do this, but we're just going to make that simple change, and we're going to see if that gives us the acceleration that we're looking for. Right? So with CPUs, it took 30 seconds. Now with GPUs, we're going to see what happens. Right? So we're going to let things kick up. We're seeing now some utilization on our GPUs. So we're seeing on the bottom right, we're seeing some plots show up. I guess I'm sort of in the way there, aren't I? And you can see that GPUs are being used somewhat, but not all the time. We're not really making those GPUs, not a heavy amount of utilization there. And these tasks are finishing faster rather than taking 10 or 20 seconds. They're running in 2 or 3 seconds. We have far fewer actual workers happening. And so in the end result, things are a bit more efficient. It took 25 seconds rather than 30 seconds. Hurrah, it's a bit better. But it's not maybe what we expected. It's not that 100x, that 10x speed boost. And so why was that? And so we might look at other kinds of information. You might look at profiling information. Right, so Dask happens to ship with a line profiler, and so we can see that about half of our time was spent in XGBoost. This is the XGBoost train method, and that's great. That's probably where we see all those green utilization bars go up. We were using our machine. About half of the time was spent, it looks like, in the scikit-learn validation module. I actually don't really know what that is, but this is not GPU accelerated. Right, we're not using our full machine here, and so we look back at our example, and we say, oh, it looks like at the top here we're using scikit-learn to make an example data set. Well, maybe we shouldn't be using scikit-learn there. Maybe that's not correct. Maybe instead we should use a library like QML or something else to keep all that computation on the GPU. Then we would try this again. So again, this is what we often see in the wild. People are excited about GPUs. They try them out. They get lukewarm results, and sometimes they stop. And you shouldn't stop. You should actually keep digging in there. If you keep digging in, you will find amazing speedups. But digging in can be challenging for a variety of reasons. First of all, like I was able to spin up, a small cluster with 5 GPUs trivially, and that was really convenient. You may not have that same infrastructure. Or if you have the hardware, your Python users may not know how to use it very effectively. And that is what this talk is about. It's about getting from having some GPUs to running some early experiments to then understanding why you might not be getting full performance. So let's switch back to slides and let's go and talk about some of those challenges. So again, right, you've seen some talk, it all sounds really great, you're really excited to try it out, but it's a challenge. It's a challenge to get right, especially with some of this newer hardware, right? It's hard to find a system that will just easily make all of your GPUs really accessible. You're gonna have to do a little bit of work yourself today because it's so new and exciting. But before we think about lots of GPUs and lots of machines on the cloud, let's start with the simplest case. You've got a single GPU. Maybe you've plugged in one of those GPU machines into a wall, you've SSH'd into it, you happen to have 4 GPUs in that machine, but you just want to use one just to get started. This is actually pretty easy, it turns out. So you can conda install most of the GPU accelerated libraries, TensorFlow, PyTorch, XGBoost, Rapids, etc. You might have to think a little bit about things like which channel to install from. So, PyTorch maintains its own builds, Anaconda maintains a separate set of builds. Depending on where you're operating, you might choose one or the other. For libraries like Rapids, there's again more choices. You just start thinking about what CUDA driver do you want to be thinking about. This is also the case with TensorFlow and PyTorch. What Python version do you want? I actually love on the Rapids webpage, there's a nice sort of option menu you can use. I've been using Rapids pretty much since it was created, or at least since that Dask integration, and I still use this on a weekly basis. So this is sort of the easiest way to install Rapids on your own. This is great, and you can read a CSV file, use some cool libraries like UMAP, or some cool algorithms like UMAP, and see some pretty good speedups. Actually, getting a speedup on a single GPU is not usually that hard. You can get a decent boost. If you don't have a GPU, that's a little bit harder. Fortunately, there are a variety of services on the web which are happy to give you a Jupyter notebook running with a GPU accelerator attached to it. Probably the most common choice here is Google Colaboratory. It's also maybe one of the more sort of messy choices. They have lots of different GPUs on there. You sort of have to figure out which one you're going to get. It's hard sometimes to get exactly the right setup. I also highly recommend Blazing SQL is a great company. They have a really nice service that's really solid to give you, a single Jupyter notebook pretty quickly with the GPU attached to it. You might also go check out Coiled. Again, this is where I work. We're also happy to launch GPUs with attached notebooks attached to clusters for you. That's what I was just using in the demo earlier. If you want to play around, it's right there. So getting started is pretty easy. It's pretty easy to play around with a single GPU. It's at scale where things really start to get more complicated. So let's take a look at that. So maybe you've bought a single machine. The machine has 8 GPUs in it. This is a diagram of a DGX, and a DGX is known for having 8 GPUs in it, right? And that's what most people buy it for, right? And so you've got these 8 GPUs. They're great. You can run that XGBoost model 8 times all on that one machine, all at the same time. But what's actually common in these machines is not just GPUs. There's a lot of other stuff in here, right? And so probably actually the biggest point of getting a high-end machine like this is the networking. So what you find is that with multi-GPU workloads, once you make all the computation really, really fast, the bottlenecks end up being in communication, right? So if computation used to be 90% of your costs, and you made it 100x faster, it's now only 10% of your costs, right? And so 90% is now in your communication. And so you actually have to be really, really careful about communication costs in order to make things really fly. And there could be communication between the GPUs with things like NVLink or NVSwitch, or it could be between different machines with things like InfiniBand. And the networking topology here is actually quite complex, right? So these 2 GPUs are attached to this interchange, which then talks to these two NICs. And so if you're on this GPU, you got to be talking to this network card. If you're on this GPU, you got to be talking to a different network card, or a different CPU. right? These boxes are kind of like little clusters in a single box. You can't just think of it as a bunch of GPUs. There's some topology you got to think about here. If, again, you care about communication, and that really depends on your workload. You might also think about communication in between your device memory, your GPU memory, and your host or CPU memory. And there's a lot of bottlenecks there. And so, in our example before, we may have been bottlenecked by just moving data from, scikit-learn and NumPy down into XGBoost to do training and then back up again. Actually, don't think that was a limitation in that case, but that is a common limitation. There's also disk, right? It could be that we can make these GPUs really, really sing, but your disk is just too slow. And so you need to start thinking about all of these different factors. It's not just one accelerator. It's a whole system. But let's say you're thinking about that a little bit. Let's say you only care about, embarrassingly parallel workloads. You don't need networking. How do you actually use this hardware? Right, so you've plugged it in, you've given it to your Python data scientist, maybe you are the data scientist. How do you actually use 8 GPUs? Like do you import GPU 1, import GPU 2? How do you do that? The most common thing we see among people who have some GPU experience is they use the CUDA visible devices environment variable. And then they run the same script many times, maybe with some configuration difference. And that helps that Python script choose a particular GPU. This ends up getting pretty ugly pretty fast. We actually recommend, if you're using Dask, there's a great project called Dask CUDA, which will look at your hardware and will make intelligent choices about mapping over it and give you some very nice Python interfaces on top of that hardware. And so you can have some function, you can map over some data, and everything will work about as smoothly as it can. You might also have more complicated workloads, right? So if you have embarrassingly parallel workloads, you don't have to care about networking too much. You can do pretty simple things, you'll be fine. You might also want to work with some more complicated library. You might want to do really big data frame joins. If you've got two big tables, you want to join them together. You might want to use gradient boosted trees at scale, XGBoost. You want to train on a large data set, so you need the device memory in all of those machines. You might need something like distributed deep learning with Horovod. All of those libraries are going to require some complicated setup, and that can be tricky. Or all those libraries can also work with Dask. And so you might use, again, the Dask local CUDA cluster to map intelligently on that hardware, map intelligently also on that networking and that device and host memory differences, and start thinking about memory management pools. And lots of those libraries will have nice Dask integration. So if you want to use that XGBoost, for example, one of the easiest ways of deploying XGBoost today is just to launch Dask and then run an XGBoost on top of Dask. The XGBoost maintainers have done a great job with the XGBoost Dask package. But even then, I'm skipping over a lot of this stuff. A lot goes into local CUDA cluster, and there still are some configurations that you may have to set. Things like memory pool size, or how do you get XGBoost and TensorFlow to share the same device memory? There are still some kinks that we're ironing out, but as we iron them out, they tend to go into this Dask CUDA package. I recommend trying it out. It's great at solving the sort of base level systems to get you up and running with a decent configuration. The next thing that we often recommend to people at this stage is to start thinking very heavily about diagnostics. You may recall that we looked at a profile plot and we saw what was taking time. We were signaled by the GPU utilization chart that we weren't using our GPU all the time. There was some idleness happening. Just having those diagnostics running while you were running code is very, very valuable. The most common thing we see today is the NVIDIA SMI tool. If you get fancy, you can sort of run this in a watch mode, and you get some nice, metrics on, what's the power usage, what's the memory usage, etc. When I first started NVIDIA, I saw a bunch of people with Jupyter notebooks on one pane and this terminal on sort of the other half of their screen. In order to resolve this, make it a little bit more smooth, the Dask Rapids team invested in dashboards that integrate directly into JupyterLab. So you can get a lot of that same information, but now real-time throwing at your eyeballs, with color and with, bars that represent things. This ends up being really helpful, again, to look at things like utilization or things like, am I using just one GPU? Am I using all my GPUs? Am I running out of RAM? Is just one GPU running out of RAM? And that can really help you understand how close you are to sort of speed of light and it can help you diagnose issues before they really frustrate you. It's pretty easy to install. This is integrates very natively into JupyterLab, very much like the Dask dashboards as well. So that's many GPUs in one box, and this is a really pragmatic way to start. When we have customers who have, they bought 10 machines, we say, great, let's start with one, get that to work for you, and then let's start thinking about many machines all at the same time. Because there's a different set of problems here, both technical and organizational. So the first thing, there's networking, right? All these machines have to be connected somehow, and you do need to start thinking about that. If you want to run libraries like XGBoost at scale, you're going to need to start thinking about not just plugging them all into the same rack, but what kind of interconnect do they have? Is that fast? Because that could very quickly become your bottleneck. And this is where, again, getting some of those higher end systems, or a system that's been pre-packaged in a nice way, can be beneficial. You can get the most out of your GPUs, making sure that they are not bottlenecked by some other system. And then there's also orchestration software, right? You're no longer SSHing into this machine. You got to manage, 9 or 10 of these. If you've got 9 or 10 of these, that's an expensive system. You probably have lots of people using it. How do you share that system? Probably you're using a system like Kubernetes or Slurm. Less likely something like Yarn. Using some job management resource provider, and you need to hook into that thing and have your users make it easy for them to request resources, especially if they don't know something like Kubernetes directly, which is rare among sort of data science, machine learning folks. Fortunately, Dask solves this problem. Dask, again, has been around for a very long time. It integrates into pretty much any resource manager, including cloud ones like Kubernetes, or cloud native things like Amazon ECS, HPC job schedulers if you're on sort of bare metal systems like PBS or LSF or Slurm, or even if you sort of have a legacy Hadoop Spark cluster around, you can use Dask with systems like Yarn. Again, Dask, you can use this with GPUs, without GPUs. Often we see people ask, hey, I've got these GPU boxes, great, Dask seems great. What about this older system I have? Can I also use Dask there? The answer is yes. We very often see Dask used sort of both on the Hadoop Spark cluster with Yarn and on Kubernetes at the same time. As people are sort of shifting workloads back and forth, it can be quite convenient. So, in principle, in theory, Dask makes the promise that you should be able to just, switch out your local CUDA cluster object with, an SSH cluster object, or a Kubernetes cluster object, or a LSF cluster object from IBM hardware. And everything should be fine, right? Dask will handle mapping over that hardware for you and present the same Python API to your users, and they will appreciate this. But that is a little bit of a lie. It does, again, get more complex than that. What we find is that this flow works really, really well in a research lab. And that's usually where companies start if they've bought 10 machines together, or if they're starting to work on the cloud. They've bought them together, they've plugged into a rack, or they've just bolted them together. And there's a small group that is experimenting with algorithms to see if this is something that the company wants to go and invest in further. This is, again, where we're seeing most companies today. And that research lab experience, you may be totally fine SSHing into those machines. You may not even need Kubernetes. You're sort of in a still very informal workflow. But eventually, when you're going to want to extend to that full company experience, that tends to be a bit harder. There's some other stuff you need to start thinking about. So at this point, you work for a large company. This is not a small investment. Eventually, you need to integrate this into some larger IT resource. You're probably going to be using Kubernetes at this stage. You're going to want to integrate into company-wide data stores, and that's going to require you to have proper authentication and enterprise authorization. You need to hook into LDAP. You need to start thinking about security, right? How do you make sure that when you are shipping that arbitrary Python code across a wire, that's not being intercepted and someone else isn't hijacking that and running code on your sensitive data? How do you maintain end-to-end security? You also need to start thinking about network speeds, software environments. Someone's going to use the new version of Rapids. It turns out to be a version conflict between XGBoost and PyTorch. And there's sort of a lot of other things that end up coming into play here, which are challenging. Not in a technical way, but just in a sort of a social, cultural, administrative way. But once you solve all of those things, things are easy again. And what we often see is that inside of companies like these, there is an IT team building some sort of machine learning platform, and they're well adept at handling these problems. It might take about a year or so, but that's sort of the plan. There's a research group, there's a sort of a long-term production group. They're both working in parallel. I want to actually quickly go back and look at our demo again. And so there's a lot of things here that we didn't talk about, right? So when we asked for machines, let's focus on this cell on this Jupyter notebook here just for a second. We asked for 5 machines on the cloud. We asked for those machines to have GPUs. That cluster also had a pre-configured set of software. I've previously defined a conda environment, some pip files on top of a Docker image, and I've had some other system build that Docker image for me. You'll also notice that this cluster spun up really quickly. It spun up in seconds, and that's because I'm cheating here, right? I'd spun this up previously, but I'm connecting to a pre-existing cluster. And so all these problems about how we allocate these machines, how we ask for them on the cloud or on Kubernetes, it's the same. Or on how we manage them. Also, if we look at this, if we look at our Dask client here, we can see that I'm connected with TLS, right? So there is some system that is tracking network security and making sure that I can directly from my laptop access these machines on the cloud securely in a way that everyone trusts, that I can play with this data and know that everything is secure and safe. And that ends up being a challenge to build that system. And again, you will eventually build that system inside of your company to use these things effectively. So that's it. Thank you for your time. If you want to read more, I recommend looking at Dask if you're interested in parallel Python at scale, dask.org. I also recommend examples.dask.org. There's tons of great things you can play with. You can see all the different kinds of integrations that Dask does. I also recommend rapids.ai. I suspect there's also several other Rapids talks at this conference. Please go check out related talks. There's a lot of fun things there. Then finally, a quick sales pitch. We've been doing this for a long time. If you need help, we're here. Coiled has services like beta.coiled.io. You can run the exact same thing I just did and play around with it. There's lots of other examples there that you can experiment with. Again, to get a taste for GPU accelerated machine learning before you maybe dive in. It's sort of nice to start in a sort of a curated experience. And then again, if you want expert help, please reach out. We're here to help. So thank you all, and I'll stop for questions.